Right, let's have a look at the CNC milling machine. I made some few more bits and pieces for it. Got these set of tooling plates, 8mm reamed hole, M5 tapped hole on a 25mm pitch, I think it was. That should make the machine much more versatile for the setting I'm given, that it doesn't have a T-slot table. Behind me you'll see all the wiring. I'm still not really keeping the covers on. I need to keep an eye on all the warning lights and things that might come up while it's been operated. I am planning on replacing the Arduino control system with a more robust system which doesn't have to rely on a computer constantly sending it information which can then get lost or misinterpreted, causing the machine to stop. As an example of a part I made the other day, I bought this 4-jaw self-centering 80mm lathe chuck. It's got a standard mini lathe backplate fitting which doesn't fit the Taig lathe. That needs a 3/4x16 UNF thread with a small register in the back. So I've turned the inside of this backplate from a piece of steel. However, I had to drill and counterbore and then put 2 flats on the side so it could be held in a vise if necessary for second operations. The counterbores were an interesting one. I didn't have the right size counterbore or end mill to mill them, so I interpolated them with a smaller end mill using the CNC machine. That all seemed to go quite well. It came out with a decent looking part. Here's the CAD model for a part I'd like to produce. It's a threading bracket for a chase screw cutting attachment. If you don't know what one of those is, check out Nick Carter's Taig lathe site. He's got a few examples of that on there. We've got 2 holes down the bottom for the rods which pull the carriage, and a larger hole up here for the holding the chase nut, I suppose you could call it, which goes along the screw and pulls the carriage to cut the thread. In order to produce compatible G-code for running the CNC machine, I use an add-on for the Onshape, which is the CAD software I'm using, called Visual Cam C, which is a free demonstration. This should open up, when it gets there, a toolpath simulation for the piece which I just modelled. I can see all my different operations. Here's the sequence of tools I'll be using, from left to right. The wobbler edge finder, a carbide spot drill, a high-speed steel twist drill, a 4-flute solid carbide end mill, and the ER16 collet chuck, which will be used to hold the cutting tools. Here's the piece of material I'm going to be using my trusty Mitutoyo digital calipers. It is 48.41mm wide and 85.30mm long. I have a feeling it is 8mm thick plate, but we shall find out. 8.11, slightly oversized. I've very quickly and roughly marked out with a permanent marker, just to make sure that if I've mixed up my coordinate systems and it starts going from right to left instead of left to right, that I can stop the machine. Going back over to mill now. The distance between the holes is a bit difficult, and I don't have a parallel that would fit well without there being at least some risk of it getting chewed up. So I just decided to use a piece of scrap aluminium which is relatively flat, certainly flat enough for the application we're using it for, and I need to use that as a sacrificial parallel to save my nice ones. So if that gets a little bit milled into, it's not too much of a problem. Just tightening up the vise now with a bar, and also got my rawhide and copper mallet just to set the part down with the vise to make sure it doesn't rattle around too much. The datum for the first set of operations on this threading bracket is this corner here, with the tools been zeroed off the top surface. I've now got the wobbler edge finder set up in the spindle, and I just need to manually move the machine until the wobbler kicks out in order to find my datum corner in the X and Y axes. Okay, quick detour there to recharge the camera batteries. I've now wobbled both in the X and in the Y axes and zeroed with that centre. I've now loaded in the spot drill and I'm going to run the program to spot the holes. Okay, so the clearance holes for the helical toolpath, which is what's coming next, have now been drilled. I've loaded up the 6mm carbide end mill, and I now need to touch off for our Z-axis 0. Now I could just do this by running the spindle and going down until I hit the part, or I could use a steel block of a known dimension and just bump the spindle down slowly until the block will no longer go into it, and then just try and find that exact position, which is what I'm going to do. So now that the large hole has been both pocketed and profiled, we're now going to profile the two small holes. Because the diameter is smaller, we can just go straight in with a profile around the edge rather than having to remove the material from the centre. So here we go. Let's measure the small holes. I did make them intentionally slightly undersized by increasing the tool diameter so as the tool thought it. Had to make a smaller circle in order to get the right diameter. So I'm now going to put my tool offset on where it should be and see where we go from there. So here's the finished part. A few scratches on the top from trying to knock the burrs off with a file. The good news is it fits the black nylon at one end. The bad news is that if we come over here, these are the twin bars which are meant to fit unfortunately, I've measured across the twin bars, and then my CAD model I made that the centre distance of the holes, with the result that the twin bars do not fit in the holes. So the part is effectively scrap, but as they say, measure twice, cut once. Right, so we've got a bit of a mess in the machine now. And the aluminium swarf that's been cut off from the piece. Fortunately the WD-40 I was using wasn't very effective at clearing the chips, so I think I need to try and rig up some other kind of system for clearing the chips, stopping them all just sticking together. Right, that's all for this time. Thank you very much for watching and hope you enjoyed the video.